What's up, YouTube? Apologies for lagging over the last month without coming up with any fresh content for you all. So today we are going to have a look at 2023 February past paper, question 5. Now, having a quick look through all of the 5 questions on this past paper, if I was sitting this exam, this is the one I would have chosen because the size of the building is relatively small. It's only 2 stories, so that just means there's less elevations and sketches, etc. that you will probably need to produce, just given the scale of the building is smaller. So you should be able to find some extra time there. And on top of that, it's got less client requirements than a lot of the other buildings. So here you can see there's only 4 client requirements. So in my mind, I would think, okay, this is a relatively small building with a small amount of client requirements. So to me, that feels like it would be quite a manageable question. So I'm just going to have a crack, as per the other previous videos, if you've been following, on my 2 scheme designs for section 1 part A. So let's have a quick look at the architectural layouts as well as the client requirements. So it's a 2-story octagonal building with a rooftop cafe next to a lake. So we'll get to some sketches above. So elevations are 50% glazed. So to me, that just limits, again, as I mentioned in the past, like where you can put your lateral stability systems, whether it's bracing or any shear walls. So structural support is to be placed within the external envelope with a maximum of 1 internal column. So that's something that, obviously we're going to pay attention to. And then here we're given the floor to floor heights being 5 meters with an internal clear height of 3.5. So the difference to that is being 1.5 meters. So that would be the maximum structural depth, including your floor and beams. So having a quick look at the architectural layouts, we've got this sort of octagonal building here with a plan of the roof level, and you can see this cantilevered balcony. So that's something like a critical detail that we'll have to come up with. So got some imposed loadings that we won't really get to in question 1 and some ground conditions here. So let's have a look at the 2 schemes that I've put together here. So as always, I come up with a little description. So my first building is a steel frame building with, I'm using the core as the lateral stability being a braced frame with braced frames in other elevations as well that we'll get to in a second. So yeah, my first scheme, I just put like a short 2-second description in terms of like what the building actually is, just to give whoever picks it up, the assessor, a good idea in terms of, okay, this is what to expect. Next, I've decided to put the ground profile, just sketch it out to give myself an understanding. So here are the parameters that we've been given, being the n values, and if you look at my foundation videos, I talk about, the simple rule of thumbs, how to convert that into allowable bearing pressure. So the groundwater tables at 1.5 meters, that will influence your allowable bearing pressures. And we've got the top meter of some topsoil here. So I've just indicated that we replace that with engineered fill. And this big sort of box here, make it really obvious in terms of what your lateral stability system is. It should be clear from your sketches in scheme 1, but I don't think it hurts to really bold it and put make it really clear for anyone who picks it up that you understand the lateral stability of the building that you're designing. So I've also decided to add this section where I'm just going to put in some key details. So I've got some composite floors, and this might make more sense when I put my scheme together. For my first scheme for this concept is, it's a steel frame building with composite floors. So if you see here, we were told that you can put 1 internal column, but for my first scheme, I decided that wasn't actually necessary. So a composite beam can actually span 20 meters. It'll be quite large. So some rule of thumbs, I've got a 1 meter deep fabricated beam, and we know with a 200 thick composite slab. So we know that the max depth was 1500, so this is 1200, so that we're satisfying the client requirements there. So it's 20 meters in one direction, and we've got 1, 2, 3, 4, 5. So that means your spacing between your steel beams is about 4 meters. So your composite slab, 200 thick, spanning one way. Yeah, we got these fabricated plate girders being 1 meter deep. Some 310 UC columns. I've placed them around in the sort of the corner of this octagon. I'm indicating where the wall bracing is. So we've got the steel brace frame in the corner here, and I didn't want to leave that as the only location for your lateral stability because that would be quite an eccentric building. So given we've been told 50% needs to be glazed, that means we've got 50% of the remaining elevation to play with to put in your lateral stability system. So here I'm indicating where the wall bracing is, and it's sort of evenly spread around the building. I've got some edge beams to close off the perimeter of the building, and yeah, as you can see here, the 310 UC columns just in the corner picking up my primary beams. 20 meters is also a really long sort of span, so for constructability I've indicated that it'll be spliced together, so I'm just showing here. This will be again sort of something to pick up in the calcs in section 2 and detail more precisely, but in your scheme design I've just shown here, okay, split it into 3 segments and showing where those splices are. So having a look at the roof level, I got a bit lazy here. I probably would put in those actual members, but so that is this sort of like little roof that they're showing here, and I've just said steel roof framing. So I probably prefer to actually do some rule of thumbs to size what those members are, but yeah, I've got some roof bracing here. And for one of the key structural elements of this building would be that cantilever on the canopy, so I'm indicating how I'm going to deal with it with sort of fly bracing. So as we'll get to in a second, obviously there'll be some hogging over these supports for the cantilever, so your critical flange will be the bottom flange. So to restrain that flange, I've put in some fly bracing, and I've just shown it in a couple of key details that I've shown here. So when it's sagging, your critical flange is at the top here, and then obviously in the cantilever, your critical flange is at the bottom, which isn't restrained by the concrete slab. So that's the purpose of this fly bracing, and you can see it here on plan. So yeah, I do think it's important that your sketches, show the layout of the building that's feasible, economical, and that you're also communicating how you're handling sort of the more technical aspects of the building. So after you show the scheme design, really important to show the vertical and lateral load pass. So here is, probably could have gone into more detail, but again, using a bit of color, showing that the vertical load pass, I've just got some simple bending moment diagrams for my 20 meter span, composite beams spanning between perimeter columns, and then coming down to my shallow foundations that I should have noted here or here, but I'm essentially saying that I don't need deep foundations and that the allowable bearing pressure within that top 150 that top 1.5 meters is sufficient for my foundation system. A quick sort of back of the envelope calc would justify that based on the tributary areas and the number of floors. Here I'm showing the key detail. This is the cantilever beam for the balcony, and that's obviously explains the location of the fly bracing here where the beam is hogging. And so that's sort of on the left hand side here is my vertical load path, And then on the right hand side here, I've indicated on, if we come back here on plan, where I put the wall bracing, it's here, 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 and then we've got a steel brace frame as well. It's described in my lateral stability box here, and here I'm just visually illustrating it with some simple arrows which show the lateral load getting back down to the ground. So that is my first building. Now my second concept or scheme for the same building, again following the same process, we put in our description. So here I've gone with the timber frame building with, now I'm going to use that central column that we were indicated that was one of the limitations. And I've got the primary beam sort of spanning from the perimeter to this central beam. I'm using a CLT floor plate, and my lateral stability is CLT shear walls, both in the core and placed around the perimeter. And I'm mixing up my foundation by actually going down into that rock layer with a piled foundation system. So again, when you're mixing up between scheme 1 and 2, make sure that they are both viable, which this one is, and also distinctly different, which, I'm using different lateral stability systems here by using shear walls, I'm using different materials, and my grid layout is sort of noticeably different with that central column now. And we'll get to it in a second. So again, just sketching out the ground profile, but here I'm indicating, okay, so I'm going to actually use this rock layer with my piles coming down to this layer. So to me, that means my slab is actually going to be suspended off the piles. So I'm going to actually leave the topsoil here. If you think that's not appropriate, leave it in the comments, see if others agree. But yeah, my opinion is if I can leave that topsoil here with an economical solution, because it's going to be expensive to excavate the whole top meter, and if I can get away with it without doing it, then why not? So coming down to some details, just some critical details. This will make a bit more sense when I actually show the scheme. So why don't I show the scheme first? So looking at a typical floor plate, here's that central column. I've sized it up a bit more from the perimeter columns because it's obviously taking a much larger tributary area, and I've also got more beams sort of spanning onto it. So there's the strength consideration to size it, but there's also the geometric consideration. So considering the number of beams I've got connecting to it, I actually need some space to connect to those beams. So I've actually got a meter square column in the center and then 600 square columns around the perimeter. So I'm using a 200 CLT floor plate. I've got 300 thick CLT shear walls. So I've placed them on these three edges of perimeter of the building. And then I've also sort of using a CLT wall within the core of my building. The roof, so what I've done here a little different, I've actually extended up one of the columns and I'm using a tension member here to support that cantilever. So instead of having beams that are just taking that cantilever as per my first scheme, I'm actually going to modify the column layer height slightly, and yeah, sort of it's a bit like a propped cantilever with a tension member. And so it's predominantly a timber frame building, but considering steel is much better in tension, I'm going to utilize that to pick up the end of my cantilever. So I've also got some secondary beams just to break up the span of the CLT. So I see the CLT spanning from my perimeter beam to the secondary beam, sort of a bit like this, because CLT floor can only really span 6 meters max, and this would be 10 meters over here. So I've broken it up a bit like this. Again, got a little bit lazy. I would prefer to size this, but I've just said timber roof framing for this roof that you can see in the architectural elevations. And on plan here, I'm really just showing that, yeah, we've got this timber bracing, this timber CHS sort of, yeah, picking up the end of my cantilever, and then glulam beam, 600 deep glulam beams below and on the perimeter here. So yeah, finally just getting into the load pass and illustrating that within your first scheme. The vertical load path, I'm showing how the cantilever works here. It's a little different because it's prop, so now it sort of sags and then hogs at the support, and then I've got some just simply supported beams running to the central column. My CLT floor also, my CLT core, sorry, will take some of the lateral loads, and then now it's coming down to that rock layer with my deep foundation, and then my lateral loads, instead of using bracing, I've got the CLT wall acting as a shear wall. So here I'm just showing the load comes in to my building, hits my two cores on an elevation, and yeah, the core does the bending, and then you get a push pull on my piled foundation. So yeah, just really clear, simple sketches using some color, making it distinctly different, and yeah, using rule of thumbs to size members, and really, yeah, just articulating the necessary and the critical elements in my scheme one. In my schemes. And then the details that I've got here, I thought it would make construction easier if the columns came with some prefabricated sort of outriggers. So that way the beams it doesn't get too congested trying to connect all those beams into the center column on site. So instead, the outriggers already come fixed to the column, and you've got a bit more space connecting those radial beams that go out to the perimeter. So that's one detail, a critical detail that I wanted to sort of communicate in my just concept sketches. And another is just showing that prop cantilever. So here I'm just showing, and these details, they're not like the details in section 2 where you're drawing to scale and it's like a IFC drawing, if you will. It's more like a sort of some key sketches. I might, yeah, maybe you consider rewording that, because details kind of makes you think it's more belongs in section 2. So here I'm just showing the glulam beam, the cantilever, or the propped cantilever member for the balcony. I got a 200 CHS member that's coming from the top of my column, and it's picking up the end of that glulam beam, and you got the CLT floor plate spanning between the two glulam beams. So I would actually have probably another over here. The CLT will have to sort of span like this. That's a bit more logical. Yeah, 5-meter spans, and then you've got your secondary beams spanning onto these 600 deep glulam beams that are picked up by your tension bracing here. So yeah, they're my two schemes that I had for question 5, 2023, section 1. If I were to choose which of the two to follow through with, make a recommendation and follow through to section 2, I would be inclined to choose this building here, because I think some key advantages of this building, being a timber frame building, its embodied carbon would be a lot less, and I think it would be quicker to fabricate, because you're not waiting for the concrete to cure that you would be waiting for when you pour your composite slabs. And yeah, all of the advantage that you could list off for timber frame buildings. And another one is the fact that I'm not excavating out this topsoil because I'm using piles to get down to the rock layer, and I'd have a ground sort of slab suspended from these piles. Yeah, so that's it. One thing that I would want to highlight is the fact that when you look at part B here, if you're going to have a crack at this, it says after construction was completed. So that means that whatever it is that, I haven't actually read this in detail, but whatever change they've requested here, you have to continue with say we choose section 2. This has been sort of constructed, so you have to keep that in mind. It's not a change to the design, it's a modification after construction. So yeah, just pay attention in terms of the time frame of when this change has been asked, because obviously, as we know, it's we can change our design before things are built, but once things are built, we're kind of left with what's out on site. So that's all I've got today. If you've got any questions, hit me up in the comments and I'll get back to you ASAP. Thanks.